So what if our curve is given not through a function y equals f of x, but through a parametric curve? Well, we're going to do something very similar to what we did with areas, namely we're going to make a change of variable. Right? So, but we're going to do it a slightly different way. So we're still dealing with the same formula, but this time x and y are going to be functions of t. So instead of pulling out a delta x, we're going to try and pull out a delta t, especially considering the fact that that's what we want our integral to be in terms of. Alright, so what we're going to do is we're going to adjust the formula that you see in front of you, not the integral formula yet, but the one you see in front of you, by using the parameter. So what we're going to do is I'm going to say, alright, the square root of delta x squared plus delta y squared is equal to this expression, and notice that all I've done, I've skipped a step here, but you'll notice that what I've done is I've now multiplied and divided each of the two terms under the root by delta t squared. And then I've taken the common delta t squared and taken it out. But now what happens is that each of those two gives me pretty much a derivative, right? The first quantity in bracket is the derivative of x with respect to t. Well, not yet, but it will become a derivative once we let n go to infinity. And similarly for delta y divided by delta t, in the limit as n goes to infinity, as the delta t becomes smaller and smaller, it will actually go to the derivative of y. So what that means is that our formula becomes the limit as n goes to infinity of the sum from 1 to n of the square root of delta x over delta t squared plus delta y over delta t squared. And again, in the limit, this becomes an integral, and the two quantities inside the brackets become the derivative of x and of y with respect to t. And you may notice that just for shortness, I've used the dot notation. Remember, x dot and y dot indicate the derivative with respect to t of x and y respectively. So very similar formula to the one we had for a regular function, only instead of having 1 plus y prime squared, we have x prime squared and y prime squared. What about polar curves? Well, they're not much different, and if you were a little bit confused by the procedure that led us to the formula for the area bounded by a polar curve, relax, we're not going to need that one in this kind of situation. In fact, all we need is to remember that every polar curve can be written, in fact, in parametric form, right? So we can write that if I have a function r equal r of theta, I can write it in parametric form as x equal r times cosine theta and y equals r sine theta. And now if I have that, now what I can do is I can use the formula we've just seen for the length of our parametric curve, because now this is a parametric curve. And so all we had to do is remember how to compute the derivative of x and y with respect to theta this time. Okay? So our formula is going to end up being what you see in front of you. The first bracket, of course, includes the derivative of x, and the second one includes or involves the derivative of y. Now, if you're starting to panic and say, oh gee, we're supposed not to worry about it, eh? Well, just pause for a second and expand those two squares and see what cancels, and you'll be pleasantly surprised. So, I mean, this is not a suggestion, this is an order. Just pause, expand both of those squares under the root, see what cancels, and see what you're left with. Yeah, that's what I want you to do. Go ahead, don't wait for me. Done. I assume you have paused, okay, and done it. So if you did it right, you should end up with this formula, right? All you end up with is just r squared and r prime squared. All the sines and the cosines will cancel with each other, and so this is the formula. Again, very easy. So notice that in the formula for the arc length of a function, we had the square root of 1 plus y prime squared. For a parametric curve, we had the square root of x prime squared plus y prime squared. Here we have the square root of r squared plus r prime squared. Very consistent, very similar to each other, so very reasonably easy to memorize. So once we go to class, we'll see how to apply these formula and these methods in specific situations.